So in this video, we're going to talk about one final type of equilibrium, which is called the solubility product, which is often abbreviated as KSP. So we've talked about K over and over again as the equilibrium expression. What we're going to learn here is how to write the equilibrium expression for solids when they dissociate or dissolve in water. So we've learned, if you have a weak acid and it's in equilibrium, we could write the equilibrium expression for this compound as Ka, because it's the equilibrium constant for the acid dissociation, H plus times A minus over HA. That should look familiar to us. We've talked about water auto-ionizes to H plus and OH minus, and that makes something called Kw, which is the equilibrium constant for pure water, which is H plus times OH minus. Just make that a little clearer. There are tons of different Ks that we can write. The new one we're going to learn today has to do with solids and how they dissolve, the solubility product. So let's say you have sodium chloride, NaCl. It's a solid. Okay? We know that it's going to dissociate into water. It's going to make the two ions, Na plus in a solution and Cl minus in a solution. So if we were to write the equilibrium expression for this, it would be K, and I'm going to use Sp for solubility product, because it's a solid, is equal to the concentration of sodium ion, Na plus, times Cl minus. I don't put it over NaCl solid because this is a solid, and we don't include solids in our equilibrium expressions. Okay? So first skill you need to be able to do is write the equilibrium expressions for solids. So here are two examples. Write the equilibrium expression for the dissociation of CaF2 and for Ag2CrO4. So this requires you to remember a little bit about our ions. So let's do the first one. Calcium fluoride, CaF2, is a solid. It's going to dissociate to form my ions, Ca2 plus, calcium. And it's not going to form F2 minus. Remember, fluorine has a -1 charge because it's in group 7 on the periodic table. So it's going to make F minus. The 2, fluorine, becomes the coefficient. That's how many moles of fluorine are going to be made when this thing dissociates, aqueous. So to write the equilibrium expression for this, it would be Ksp equals concentration of Ca2 plus times the concentration of F minus to the power of 2. Okay? For part B, this would be Ag2CrO4, solid. It's in equilibrium. I need to write the equation. It's going to form 2 Ag plus because silver has a +1 charge. That's not one that you have to have memorized, but it might be a good one to know. It would be given in a problem, though. And then CrO4, in order to balance the charge, this has to be -2 aqueous. So the equilibrium expression for this would be Ksp equals concentration of Ag plus squared times the concentration of CrO4 2 minus. Okay, so writing expressions from solids. It's easy. The solids are never included, so it's pretty straightforward. The only thing you got to watch out for is little subscripts become coefficients because the moles are getting reciprocated in that way. There's two types of problems that we have to do with solubility product. Basic type of problems. One where the KSP is given and you're asked for concentration. Another word you might hear for concentration is they ask for the solubility. Just be aware that solubility and solubility product are two different things. Solubility is concentration. Solubility product is KSP. The other ones are if the solubility are given and they ask for the solubility product. So one or the other. We're going to do one example of both. So, first one. The solubility product, KSP, for AgCl is 1.6 times 10 to the negative 6. What is the concentration, solubility, of each ion? So first step, write the equation. AgCl solid is going to dissociate, Ag plus aqueous, Cl minus aqueous. So the constant would be KSP is equal to the concentration of Ag plus times the concentration of Cl minus. Now what's the problem asking for? It's asking for the solubility of each ion. That means this value and this value. So the way we need to do this is we plug in our K, 1.6 times 10 to the negative 6. But now what do I plug in for these values? There's no ice table involved. There's nothing like that. We don't know the concentration of Ag+. So it's X. Okay? It's going to be 1X because the coefficient here is 1. Because every time this dissociates, it's going to split up into 1 mole of Ag and 1 mole of Cl. So that's why I put a value of 1X here. For Cl, the coefficient is also 1, so I'm going to also plug in 1x as my unknown value. Okay. If these coefficients were 2's, 2Ag and 2Cl, then I would plug in 2x times 2x. But that's not the case for this one, but something to be looking out for in the future. So what I know now here is that this is going to be 1.6 times 10 to the negative 6 equals essentially x squared. So if I square root both sides, I'm left with x is the concentration of each ion as 1.3 times 10 to the negative 5 molar. Cool. So why is that cool? Why is that beneficial? Well, let's say you're dissolving a solute into water, in this case silver chloride, AgCl. If we know it's KSP, okay, we know exactly what the concentration of every one of these ions, here's the Cl, here's the Ag. We know exactly what the concentrations of each one of them will be once that gets dissolved. Again, one thing to watch out for is if you change the temperature, that's going to change the solubility product. K is only true at whatever the temperature is that it's measured. So this is the value of the concentration of Ag plus and the concentration of Cl minus. The other type of problem you have to do would be if you're given the concentrations and asked to solve for KSP, like here. The solubility, again, not solubility product, this means concentration, of MgOH2 is 1.3 times 10 to the negative 4th. Based on this information, what is the solubility product of MgOH2? So, again, write the equation first. MgOH2 as a solid dissociates into water. It's going to form Mg2 plus. Magnesium is in the second column of the periodic table. OH minus, aqueous. However, since I have, forgot the 2 there. Since there are 2 of these, I need to put a coefficient of 2 in front of the OH. So my KSP, my expression, would be the concentration of Mg2 plus times the concentration of OH minus squared. Now, this is where things get a little tricky. We're told that the solubility of this compound is 1.3 times 10 to the negative 4th. Okay? So what does that mean? That means that the concentration of these ions is a factor of 1.3 times 10 to the negative 4th. Since when this compound dissociates, it makes 1 mole of Mg and 2 moles of OH minus, we need to take those coefficients into account when figuring out the value of each one of them. So since this is the concentration of MgOH2, the solubility, that's going to be the concentration for every 1 mole of an ion. So since I only have 1 mole of the Mg2 plus ion, the concentration of this ion is 1.3 times 10 to the negative 4th. However, for hydroxide, since every time this compound dissociates, it makes 2 moles of hydroxide, the concentration of hydroxide is not going to be 1.3 times 10 to the negative 4th. It's going to be 1.3 times 10 to the negative 4th times 2, because I'm making 2 moles of it every time. So basically this number times 2 would give you 2.6 times 10 to the negative 4. Which makes sense, because I'm making twice as many ions of this as this when magnesium hydroxide dissociates. To give you a picture of that, just think visually. That's kind of saying like, okay, here's my Mg2+, and it's connected to, an OH and an OH. And so when this dissociates, it's making OH minus, and Mg2+. So you can tell you make 2 moles of hydroxide for every 1 mole of this compound. So that's why I have to double the amount, because the coefficient is 2. Here, it's relatively straightforward. Just plug in the numbers that you have. KSP is equal to 1.3 times 10 to the negative 4th times 2.6 times 10 to the negative 4th squared. If I go ahead and do the math, make sure to square this first before you multiply it by the final answer, but you should get 8.8 times 10 to the negative 12th is the solubility product of magnesium hydroxide. Notice this exponent is 10 to the negative 12th. That means this value is like 0.000000, with 11 zeros, it's not going to be accurate. 88. Much, that's super messy, but much less than 1. So very, very little of this is going to actually dissociate. So a very small amount is going to make product. Another way you could have set this up and thought about it with x's is if this is like 1 times x, the concentration of this would now be 2 times x to the power squared, where x is the solubility that's given, boom, that I would plug in here, and then I would do the math the same way. So we got to feel comfortable doing either type of problem, either solving for KSP as in here, or solving for the solubility, the concentration of each ion here. Be careful, solubility and solubility product are not the same thing.